And very useful tool. Wherever you are going to go, you are going to use them. Any structure like this, Cn x minus a to the power of n. Okay. This is called a power series. A power series around a. Okay. What is the difference between this kind of series with the numerical series that we know? First of all, this x is going to be a variable that we are going to be able to plug some numbers inside of it. Okay? And if we plug some numbers here instead of x, then we are working with the case of real variables. Or you can also select this as a complex variable, which we are going to show it by z. Then we are working with power series. If we want to write the terms here, okay, one step, what will happen here? Instead of n, I will give 0, right? So this is going to be c0, x minus a to the power of 0. What is x minus a to the power of 0? 1. So c0 is our first term. What about our second term? C1 x minus a. Okay. What is the next term?
C2.
C2
x minus a
to the power of 2, etc. Okay. We see three different things here. First of all, we have these terms x minus a to the power of 2, x minus a to the power of n, right? Here our x is going to be our variable that we are going to be able to plug some numbers inside of it. This a is the point that we are writing the power series. Okay? We will see some examples and you will understand what is this point a. And our coefficients are these numbers c0, c1, c2, etc. Okay? Again, this can be complex numbers, these can be real numbers. Okay? In most of the cases, we will talk about the real setup, but we will also talk about complex cases as well. Some examples. Look at this. X to the power of n divided by n. Let's start n from 1. Okay. Question. Is this a power series or not? And if it is a power series, around which point it is a power series? Which means that what is your A? What is your CNs?
I think it's power series.
Yes.
Because, but here,
what is our point A?
A is
Around which point we are writing this power series? 0, right? It is x minus 0 to the power of n's. Okay, A is 0. What is our coefficients? CNs? 1 over n. Okay, so this is actually a power series. What about other examples? X to the power of n factorial. Or let me write it around some other point. Where is it? Z minus 3 to the power of n. Here z can be a complex number as well. Okay? Is this a power series or not? It is. What are the coefficients? What is our coefficient Cn? Yes, 1 over n factorial. What is our center? This point A? 3. If it was z plus 3, then it was going to be around the point minus 3. Okay? Look at this. power series or not? Around which point it is a power series? It is around 0. What are the coefficients? A0 is point, A is 0.0, and our coefficients are 1. Now, this is 1 plus x to the power of 2, x to the power of 3, etc. Right? If I want to represent this in another form, what should I do? Is this something very similar to geometric series or not? It is, right? So what will happen to this? Look, instead of this r in the geometric series, okay, if we plug x, what will happen? Can I represent this as 1 divided by 1 minus x? It is exactly the same thing for the geometric series, right? What is changing? We have here another shift in our perspective. First of all, when we are looking to geometric series, we had a fixed number, right? We had a fixed number in the base, and we were not changing it. It was a fixed number. But here, we are behaving with this series like this x can change, which means that you can plug different numbers here. Okay? Can instead of x you plug 0? Yes, of course, right? It is a geometric series, and to which number it is going to be convergent? Not 0. Yes, it is going to be 1, because it is going to be 1 plus 0 plus 0 plus 0 plus 0. Don't forget this one. Okay? If you plug 1 divided by 2, for instance, in x, are we going to get another number out? Which means that is the result of this series going to be a number? If we give 1 over 2 instead of x. Is it or not? Which means that it is going to be convergent at that point, right? For x equal to 1 over 2, it is going to be convergent. And to which value it is going to be convergent? Yes. Or don't give the number, just say that since it is going to be 1 over 2, it is going to be 1 divided by 1 minus 1 divided by 2. Which, if you do the calculation, it is going to be 2, right? Good. What happens if instead of x, I plug the number 2, for instance? Will I get another? Yes, it is going to be divergent. So I'm not going to get a real number out of it, right? Which means that if I'm going to take this as a function, okay? At some points, I'm able to give number to this and get a number out of it. And this will happen at the points that this series is convergent. And at some points, when I'm plugging some numbers, I will not get a real number. I will get positive infinity. Okay? And positive infinity is not a real number. Which means that I cannot define a real number for that values. This is the change in perspective that we are having. If we are going to take this as a function, can we really define it in a well and good behaved manner? Which means that for which values of x, we can say that, okay, this is going to be a function. Here, for which values of x, I can plug here and I get a real number. When our values of x, since this is a geometric series, when their absolute value is less than 1. Or when our x is between -1 and 1. Okay? This is a valid function. Now, since we are going to work with this power series as functions, again another matter comes to our mind that we need to ask about. First of all, look at this function. 1 divided by 1 minus x. Okay? At which points is this function defined? Yes, the whole real line except the point 1. Okay? Can you please take out your phones, go to Desmos, Desmos graphing tool. And please draw the graph of this function. Y equal to 1 divided by 1 minus x. Could you plot this? Y equal to 1 divided by 1 minus x. This function. Okay? You see its graph like? No. Let's come to the left-hand side of this equality that we have written here. Okay? Can you please draw the first term of this? Or can you come to one new line and plot y equal to 1? Can you plot 1 plus x? Then can you plot 1 plus x to the power of 2? You see where I'm going? Can you please plot a few more and see what happens? Can you please let me know what you are seeing? Or what is happening? As you go on more, and as you select more and more terms from here, from this series, you are actually getting better and better approximations for this function, right? But around on the whole domain of this function, on the whole of R, or around a point, which is going to be the point 0. Is this approximations that you are doing is getting better and better approximations for the graph of this function around the point 0 or not? It is going to be like that, right? What happens for the points that are not in the close neighborhood of 0? For instance, what happens around the point x equal to 2? This is something meaningful. But what will happen to this kind of functions that you are drawing? You see, there will be a huge difference between them, right? What is the case here? What is happening? When you are writing this equality, you are claiming that this function is equal to this power series, right? But when it is true, for which values of x? It is going to be true even if you add infinitely many of them. It is going to be a good approximation around the point 0, x minus 0, such that. And how much to left and right of that point 0 you can go and you have still a good approximation? This thing that we have here, that we know from geometric series, it is saying that around the point 0, you can go 1 unit to left of it or to right of it. And you have still good approximations if you are working with this kind of things for this function. Outside of this interval, what will happen? You have not good approximations. And even the equality is not true. So this is very important to remember that. When we are working with this kind of power series, they are going to be local objects. Local objects or local approximations to some functions. Okay? But the thing is that this locality is coming around the center that we are opening up or writing up this power series. Around which point this is a power series? Around the point 0. So this is going to be locally around 0 we defined. What about outside of some interval of 0? Maybe it is going to be meaningful, maybe it is going to be meaningless. Okay? This is what we are going to discuss actually. But you see my point, right? What is happening? We have a function, we can represent it as power series. And maybe it is good approximation, maybe not. We are trying to find representations for some functions that they're representing them in a good manner, and vice versa. If you have a power series, okay, and if you want to look at them as some functions, okay, like this one, which is a geometric series, instead of fixing this value, if I change these values of x's, can I take this as a function or not? These are the main questions that we are going to discuss. Okay? So it is clear what's happening, right? No. Assume that we have a power series like that. Cn x minus 8 to the power of n. Okay? If I plug a number instead of this x, what will this turn into? This will turn into a numeric series, right? If it is a numeric series, then we can ask about its convergence and divergence, right? The question remains for us is this. For which values of x I can plug inside of it, and I still have a meaningful function? I mean, for instance, if I give 2, it is convergent. If I give -1, it is convergent, and so on and so on and so on. What kind of a set is it going to be? This values of x that are going to make our series a meaningful numeric convergent series. This is the question. If this x is going to be bigger than a, then this is going to be a positive number. If it is going to be smaller than a, then this is going to be an alternating numerical series. Okay, we have positive numbers and negative numbers. Okay, so it doesn't matter. But the thing is this: can I give some scattered values of x, or are those values that the series are convergent have a very smooth structure for them? The thing is that, let me call this star. If a star is convergent for C, let's take it not equal to A, okay? Then it is convergent for all x or z or whatsoever, such that their distance from A is less than C's distance from A. Or in much simpler terms, let's have a power series which is defined around the point 0. Okay? If I select a non-zero number, okay, and if this Cn, c to the power of n, is convergent, what can I say is this? It is also convergent for all x with absolute value of x less than absolute value of c. If I select a number c, plug it here instead of x, for instance the c here, okay? And if the series is going to be convergent, then for all of the values that are going to live here, okay, if you plug any value from here inside of this power series, this series is again going to be convergent. Not only convergent, it is going to be absolutely convergent, by the way. Absolutely. What about the values to the left of it? It is also going to be true. So if this is going to be minus c, I can also plug any values from here and still have this convergence. Okay? Look at this. This is again the same thing. I have this r, or you can also look at it in the complex plane. Let me first start from here. I will go to complex plane as well. This is our 0. If I select a c, okay, this minus, positive, whatsoever, I don't care. Okay, just select the c, okay, plug it here, and if the series is convergent, then around this point 0, if you have an interval with this minus c. For all of the values that are living here, okay, this series is again going to be convergent, and it is going to be absolutely convergent. Why, by the way? Can you convince yourselves? If I take a value from here and plug it here, okay, in absolute value terms, it is going to be Cn x to the power of n smaller than or equal to Cn c to the power of n, okay? And if the Cn c to the power of n is a convergent series, this series is going to be bounded from above, right? By this one, so it cannot blow to positive infinity. So this must also be a convergent series, okay? This is a loose statement of what is happening, but it is what is happening here. What about if instead of this x, we select a complex variable, okay? If this is going to be our a, okay, we can always find a neighborhood around this such that for all complex values which are going to be selected from here, our power series is going to be absolutely convergent. For all the values outside of this disk, it is going to be divergent, okay, or meaningless. That is why we are saying that power series are actually local functions, because around one point, locally you can define them. Maybe this radius that I'm going to define what it is, maybe it is going to be so big that it is going to be the whole set of complex numbers or real numbers, but it is not the case that in all of the series it is going to be the whole plane. Okay? These objects are local objects. Good? This brings us to the idea of radius of convergence and interval of convergence, or disk of convergence for complex numbers. Radius and interval of convergence. If you have a power series like this, z minus a to the power of n, okay, z here can be a complex number, it can be a real number, it doesn't matter which one you are easier that work with them. There exists a positive r, okay. When I'm saying this r is a positive number, can it be a complex number? It cannot be. Because in the field of complex numbers, we did not have positive complex numbers, negative complex numbers. It is a field that cannot be ordered. When you're talking about this positiveness, it is a real number actually. Okay? There exists a positive number such that, let me call this number star, is convergent for all z with this, okay, around the center. What is the geometric meaning of this, by the way? This is the set of all points such that their distance from the point A is less than r, which is actually this disk with the radius of r. Okay? If inside of this disk or inside of this interval that we have on the real line, you select any z and plug it in your series for all z. Absolute convergence also. Okay? And it is divergent for all z's such that their distance from A is bigger than R. Okay? Let's see some examples. Let me start with the simplest case, x to the power of n. Okay? Is this a power series or not? And is it starting from 0? It is going to pass to infinity. This is a power series, right? Around which point it is a power series? Around point 0. Okay. If I plug 1 over 2 here, 1 over 2 here, is this going to be a convergent series? So it is meaningful. Which means that here, between minus 1 over 2 and 1 over 2, if I plug any number here, this is going to be again a convergent series. My question is this. Is this 1 over 2 the biggest number that I can write here? For instance, what will happen if I give, I don't know, a little bit to the right of 1 over 2? If this is 0, if this is 1 over 2, if this is 1, if I select the number from here, okay? What will happen if I plug this number inside of this series? It is again going to be convergent, right? Because it is still less than 1, and we know that from geometric series it is going to be. Which means that I can extend this 1 over 2, again, push it. Is there a limit that I cannot push it any further? If I can arrive to that thing, that is going to be our radius of convergence. And the interval that I can give values from there into the x is going to be our interval of convergence. Okay? But how can we find this R? The property of this R is that for values smaller than that, convergence bigger than that, divergent. Okay? How we can really find this value of R? We can find this value of R, or the radius of convergence, by using ratio test or the root test. Okay? Radius and interval of convergence can be found by ratio or root test. How? Let's assume that we have x minus a. Let's assume that we have this kind of a series. Okay. Let me also show this as an. Here I mean that this whole thing, I'm showing it with an. And when I'm writing C, I mean that I'm not working with this x's and I'm only working with coefficients. Okay? Now, if we plug some x's here, some values here, this is going to turn into a numeric series, right? And if you want to know that, if you want to be sure that this series is going to be convergent, what was the condition from the ratio test that we had to have to be sure that this is going to be a convergent series? We need to have this limit of an plus 1 divided by an less than 1, right? The thing is this. If you take this whole thing and calculate this limit and continue, it will give you the interval of convergence. And if you work with only the coefficients, okay, we are going to define this number L as limit of this Cn plus 1 divided by Cn, okay? And in this case, our R is going to be 1 divided by that limit. You will see why it is going to be 1 divided by that limit. I will just solve some examples and you will see what's happening, okay? But there's 2 points that we need to be careful here. This value, this L, which is coming from our limit, it can be 0, it can be positive infinity. If our L is 0, then we are defining this R as positive infinity, and if this L is going to be positive infinity, then we are defining this R as 0. Okay? Is this a power series or not? Around which point it is a power series? Around point 0. This is x minus 0 to the power of n divided by n. Right? This is 1 over n, x minus 0 to the power of n. You need to always convert it to the general form of the series and try to understand what's happening. We had Cn, x minus a to the power of n, right? Since this is in this form, yes, this is a power series. What are this point A? 0. So this is a power series around the point 0. Okay? Now, 2 things from here. What is our coefficients? What's our Cn? Here it is 1 over n. If I want to take the whole thing, and I call it an, what is this an? X to the power of n divided by n. Let's assume that we have plugged some values here, okay? And we have a numerical series. I want to understand about the interval of convergence and the radius of convergence. What should I do? What does, for interval, what does the ratio test tells us? Tells us that we need to have limit of an plus 1 divided by an be less than 1. Okay? If this is satisfied, this is going to be a meaningful thing, right? What is an plus 1? Here, in x to the power of n divided by n, instead of n, we write n plus 1. So it is going to be x to the power of n plus 1 divided by n plus 1. And what's our an? This thing itself. X to the power of n divided by n. I want this limit to be less than 1. Okay? How can we simplify this? X to the power of n plus 1 with this xn. So it is going to be just x. And this n is going to come to denominator, n plus 1 is going to. So it is going to be n times n plus 1. And we want this to be less than 1. Okay? From here, can I write this as limit of absolute value of x times n plus 1 less than 1? Can we do this? I'm just separating them. X and n divided by n plus 1. And since n divided by n plus 1 is a positive number, I can get rid of absolute values as well. Now, look at this. Here we are taking limit with respect to n, right? Is this x anyhow related with n? No. So it is behaving like a constant number. So we can take it out of limit. Which means that this is going to be absolute value of x times this limit less than 1. What is this limit? Limit of n divided by n plus 1. If we want to calculate this limit, if you put positive infinity directly here, it is going to be positive infinity divided by positive infinity. Something meaningless. And we have talked about that. If we have polynomials and we want to calculate their limit, we are just taking the ones with the highest degree terms, right? So this is going to behave like n divided by n. Cancel n's, it is going to be 1. What is the limit of 1? 1. So this is going to be absolute value of x times 1 less than 1. Okay? Look to this. What do we have? This means that for all values of x such that their absolute value is less than 1, this series is a meaningful series. Okay? We can write this as also as x minus 0 less than 1. Or you can write it as x between minus 1 and 1. Okay? What about the values of this series at the point 1 and minus 1? If you plug 1 instead of x, what kind of a series is this? It is series of 1 divided by n, which is a harmonic series, right? And it was convergent or divergent? Divergent, yes. What about minus 1? If you plug minus 1 here, is it going to be convergent or divergent? Alternating series, and it is? Convergent. Based on Leibniz's test, it is going to be convergent. So at the boundary points, it may be convergent, it may be divergent. We have no idea. Looking at this and having our center as the point 0. What is our radius now? Around this point 0, how much we can go to left and right? 1. So our radius is 1. Okay? Here we have worked with the whole terms of the series. Okay? What happens if you only work with the coefficients? Okay? The second thing, for the radius, it is going to be the same thing. But let us try and see. For radius, or our second approach, we are just going to define this L as limit of ratio of coefficients. Okay? What is the Cn plus 1 in this case? Please speak up. 1 over n plus 1 divided by 1 over n, which is going to be equal to limit of, since they are all positive, I can get rid of absolute value as well. This is going to be limit of n divided by n plus 1. And what is this? 1. Since L is 1, what is our R? 1 divided by L, which is here 1 divided by 1, which is 1. Which means that our radius is going to be 1. Now, if our radius is 1, what is my interval of convergence? For which values of x? I am sure that this is going to be something meaningful. We need to first find out around which point this is a power series, or find out the center. And what is the center for this power series? It was the point 0, right? Which means that around point 0, okay? If you have a circle of radius 1, which it is going to be this interval from minus 1 to 1. For these values, it is going to be convergent. What about values outside of this? Here and here, it is going to be divergent. Okay? This was going to start from 1, by the way. None of you have mentioned it to me. Because, yeah, here if I plug 0, it is going to be meaningless. It has to be starting from 1. What about this one? The series x to the power of n divided by n factorial. Is this a power series or not? Around which point it is a power series?
0.
So our center A is 0. What is our coefficients? 1 over n factorial. What is an? If we take the whole thing, it is going to be x to the power of n divided by n factorial. Okay? Now, can you please use the ratio test in order to find the interval of convergence? If you work with this, you will get the interval of convergence. If you work with this, you will get to the radius of convergence. Work with any one of them you like, and let's try to work out the interval of convergence first. Okay? What I need to do, I need to have limit of an plus 1 divided by an less than 1. For the values of x's, such that this limit is less than 1, I am sure that my series is something meaningful. Okay, it is going to be convergence based on ratio test. So, what is happening here? What is this limit of an plus 1 divided by an? What is an plus 1? What is an plus 1? Please speak up louder. X to the power of n plus 1 divided by n plus 1 factorial. And an is x to the power of n divided by n factorial. For values of x's, such that this limit is going to be less than 1, this is going to be a valid power series. Okay? We can. What about this? How can we simplify this? This x to the power of n plus 1 and xn, they just cancel each other and we have an x. This is going to be absolute value of x. And it does not depend on n. I can take it out of the limit. So this is going to be absolute value of x times limit of. The rest are positive numbers. I can get rid of absolute value as well. Just parentheses is enough. And what is going to be? 1 multiplied by n factorial. n plus 1 factorial. I want this whole thing to be less than 1. Okay? What is this equal to? Yes, we can write this as n plus 1 times n factorial. Right? It was the definition of factorials. These cancel. And what do we have? Absolute value of x times limit of 1 divided by n plus 1. We need this to be less than 1. What is this limit? 1 divided by n plus 1?
0.
It is going to be 0. So, absolute value of x times 0 should be less than 1. Okay? For the values of x, such that this is true, this is a meaningful series or a convergent series. Now, question. For which values of x is this true? For every value of x, right? It is true. No matter which real number or even complex number, the same logic. You plug here, it is going to be multiplied by 0, which is going to be 0, and 0 is always less than 1. So for which values it is convergent? For all of the real numbers or for all complex numbers. So our interval is going to be R. Okay? Or C. Okay? What was our second approach? Second thing? Instead of working with the whole thing, just go work with the radius and find the radius. So, okay, the second thing. What is our L? How did we define this L? As the limit of Cn plus 1 divided by Cn. Which is going to be what? Limit of. What is Cn plus 1? 1 over n plus 1 factorial. And this is 1 over n factorial. Which is going to be limit of, again, if you do this, this is going to come here, this is going to come here, they will cancel out, this is going to be limit of 1, n plus 1, which is going to be now 0. We had our radius 1 divided by that thing. Why? You see here, what is happening is this. We have this absolute value of x or whatsoever multiplied by this limit of ratio of coefficients less than this one, 1. Which means that this absolute value of x is going to be less than 1 divided by this limit. That is why we are defining this r equal to 1 divided by that limit. Okay? Now, if our L is 0, our r is going to be 1 divided by 0, but we have had this notation, right? Since 1 divided by 0 is meaningless, we need to define this r as positive infinity. Okay, so our R here, our R, this means that our R is going to be positive infinity. Now, question. I only have the radius of convergence. Okay? What about the interval of convergence? If I want to find the interval of convergence, what should I do? What was the center that we were writing this power series? If around 0, you have a circle of, or an interval with radius of positive infinity. Okay? What will happen? You will have all of these values. And it is going to be what? The whole of R. Again, the same result. Is this a power series or not? Around which point it is a power series? Are you sure it is 1? 1 over 2. Kerim'di değil mi? Why? Here we have a coefficient for x, okay? We need to have the general form of it. X minus a to the power of n. So in order to make this as x without any coefficients, what should we do? We take a factor out of 2 and write the rest, right? So this is going to be like n from 1 to infinity of 2 to the power of n, x minus 1 over 2 to the power of n. Right? Is this clear what's happening? You need to identify an and cn, right? What's our an? Or the general thing? The whole thing itself. 2 to the power of n divided by n, x minus 1 over 2 to the power of n. Or you can work with the coefficients. What are the coefficients? 2 to the power of n divided by n. If you work with this thing, you will get the interval. If you work with this thing, you will get the radius. Then after finding the radius, you need to come and around this point, around the center 1 divided by 2, you need to draw a circle or an interval with that radius in order to find the interval of convergence. Can you please do the calculations? Let's directly work with this AS so we can see what is happening with the interval. Okay? If I want to have this as a convergent series, I need to have limit of an plus 1 divided by an less than 1, right? So let's do it. What is limit of an plus 1 divided by an, which I need it to be less than 1? You need to write it right. It is going to be limit of. What is your n plus 1? Here, instead of n, you need to write n plus 1, right? So it is going to be 2 to the power of n plus 1 divided by n plus 1. Okay? And this is x minus 1 over 2 to the power of n plus 1 divided by 2 to the power of n divided by n, x minus 1 over 2 to the power of n. I want this whole thing to be less than 1. Okay? First of all, this x minus 1 over 2 to the power of n plus 1 and this one here, they will cancel out and I will have only a x minus 1 over 2 here, right? Which inside absolute value, I can take it out of the limit, which is not going to be depending on n, so I can take it out. So this is going to be absolute value of x minus 1 over 2, okay, times limit of what? 2n plus 1 divided by n plus 1, 2n divided by n, right? I need this to be less than 1. Look at this. Is this limit of cn plus 1 divided by cn or not? Okay? I want this whole thing to be less than 1. Okay? So I need to take this to this side, right? This to this side. If I call this L, this interval is going to be less than 1 divided by L, right? That is why we are defining R as 1 divided by L as well. Because we are taking this and bringing it down here. That is why. Okay? But anyhow, let's continue. I need to have this thing satisfied. So x minus 1 over 2. What is this limit equal to? We have 2n plus 1. They will cancel out. We have a 2. We can take out this 2 times. Then it is going to be limit of n divided by n plus 1. I need this whole thing to be less than 1. Right? What is this limit equal to? 1. So this thing times 2 must be less than 1. Or for the values of x such that if you put it here, then multiply it by 2. If that thing is less than 1, our series is going to be something meaningful. Okay? I can write this as 1 over 2. What does this mean? This means that around 1 over 2, if this is 0, this is 1 over 2, we can have an interval with radius 1 over 2, which is going to be this one and this one. So for these values, it is going to be convergent. For these values, it is going to be divergent. Okay? Working with this whole thing directly gives us the interval of convergence. What happens if we only work with the coefficients? Let's also do that. How did we define our L? We define our L as limit of Cn plus 1 divided by Cn. Did you do it? You have done it correctly?
Yeah.
What was this limit?
2.
You get a point. Okay? Remember. What is this going to be? This is going to be limit of this exact thing that we have written here, right? Because they're the same things. It is going to be 2 to the power of n plus 1 divided by n plus 1, 2 to the power of n divided by n, which is going to be equal to 2. If this is 2, what is my r? Our radius of convergence was 1 divided by L, which is here going to be 1 divided by 2. Now, working with coefficients, I only have the radius of convergence. Based on this radius of convergence, how can I get to know what is the interval of convergence? In order to know that, first I need to understand what is my center that I have written this power series. Around which point was this a power series? 1 over 2. So around point 1 over 2, if you again open up a radius of 1 over 2, which means that this one's here up until 1. Okay? This is going to be your interval. Is this the same thing or not? The same thing. Because we're actually doing the same thing. But this is a series. This is a series around 1 over 2. Okay? That is why I'm writing this 1 over 2. Because I want to know the center about power series. By chance, the radius of convergence for this series has also turned out to be 1 over 2. That is why this is 1 over 2, 1 over 2. The radius must have been, I don't know. If you place some other number here, if it was 3 to the power of n divided by n, x minus 1 over 2, I think it was going to be a radius of 1 over 3. Okay, so around 1 over 2, you had to go 1/3, 1/3, to left and to right to have the interval. Okay? One more example. Is this a power series or not? Why not? It is right. What is the coefficients? N factorial. So our Cn is n factorial. Around which point is this a power series? Around the point 0. Okay. Can you please find the interval of convergence or the radius of convergence? Okay. We have two approaches, right? We have two approaches. Either we work with the whole thing. Let's do it. I want what? Limit of an plus 1 divided by an to be less than 1. So what I need to have? What is my an plus 1 here? n plus 1 factorial. n plus 1 factorial x to the power of n plus 1 divided by n factorial x to the power n. I want those values of x's such that this is true. What is this then? This is going to be absolute value of x to the power of n plus 1, divided by x and is x. In absolute value, we get it out. So we have absolute value of x times, or we can also have it here. Let me have it here, because it's going to be limit of absolute value of x times what? n plus 1 times n factorial. Keep this n factorial, they cancel out, so we have n plus 1. I need this to be less than 1. Okay? For which values of x this limit is less than 1? If x is 0, if x is 0, this will be 0 times n plus 1, which is going to be 0. And limit is going to be 0. And we will have 0 less than 1, which is something true. If x is not equal to 0, what will happen then? This is going to be a positive number multiplied by this n plus 1, which is tending to positive infinity. Then this limit is going to be positive infinity, and we will have positive infinity less than 1, which is not a true statement. Okay? Which means that this is true only for which values? X equal to 0. True for only x equal to 0. What does this mean? This means that here we have this point 0. At this point it is convergent, and it is convergent to which value?
0.
Outside of it, it is divergent. Okay? We can work out about the radius. What is the L that we are going to calculate for the limit? It is going to be limit of Cn plus 1 divided by Cn, right? Which is going to be limit of n plus 1 factorial divided by n factorial. And what is this limit equal to? Positive infinity. If L is positive infinity, how did we define our R? 0. Now, I have the radius. What was the center for this power series? 0. So around 0, you go a 0 to right? So at the point 0, you have convergence. At the other points, you have the divergence. Okay? Is it clear? Good? Okay. If we have two power series, how can we create new power series from them? Okay? Operations on power series. Let's assume that you have our AX as this power series, A and x to the power of n. Okay? I'm centering them around 0 because it is much more easier and simpler to write. But you can shift them around any point, and let's take Bx as Bn x to the power of n. Okay? And these are going to be defined on this interval. They have the same interval of convergence. Okay? Ax plus minus Bx. What can you say about this? If we add two power series, which means that we are doing this an plus bn or minus bn x to the power of n. I think this is ending. I should not continue writing with this. What will happen to this? Is this a power series or not? This is going to be a power series. You can add those power series, and is the ratio of convergence going to change or not? It's going to be the same. Because what is happening is this. You are working with this one and you're working with this one. And then you're adding them together. Okay? In the cases that this an and bn are positive, because you can have troubles over there. But when you're adding power series, you can be sure that their ratio, their interval of convergence is going to be at least the smallest of both of the ratio of convergence of these two. Okay? In the case when an and bn are positive, I think that we can be sure about this. Okay? What about if we multiply it with a c, with a number? Again, that is going to be a power series. And how is that power series? C times ax. How is it defined? It is defined by multiplying the c inside each one of these. So it is going to be c an x to the power 2. Again, it is a power series. Okay? If ax and bx are absolutely convergent, then ax times bx is convergent on the same interval. What do we mean by multiplication of two power series, by the way? How do we multiply two series? This ax times bx is going to be represented as, what is my ax? It is a0 plus a1x plus a2x2, a3x cubed plus the rest, multiplied by, or let me write this like this, I need some space, multiplied by b0 plus b1x plus b2x2 plus the rest. What I'm claiming is that this multiplication is also going to be a power series. Okay? And what is that power series? What are the coefficients of these? In case that this ax and bx are absolutely convergent, you can just term by term multiply them to each other. Okay? Which means that we are taking this a0, multiply it to all of these terms. Then take a1x, multiply it to all of these terms. Take a2x2, multiply it to all of those terms. Okay? If you do this, what is the term that has no x with it? I need to select something from it that has no x, no x. So it is going to be a0, b0 plus. What is the coefficient of x? We want to select something from here that does not have an x, and something from here that has an x. It's going to be a0, b1x, right? Or select something from here that has an x, and something from here that has no x. So it is going to be a0 times b1 plus what? a1 times b0 x. Plus, what about the term that has x to the power of 2? What is the coefficient of x to the power of 2? How can we get it? We need to select from here a term that has no x, from here a term that has x to the power of 2, which is going to be a0, b2. Something from here that has an x, and something here that has an x. a1x times b1x, what will be? a1, b1, x to the power of 2. Or something from here that has an x to the power of 2, and something from here that has no x to the power of 2. Then what is it going to be? a0, b2 plus a1, b1 plus a2, b0, x to the power of 2 plus the rest. What will be the general term? If I want to write the nth term here, what is the coefficient of x to the power of n? This is going to be a0bn plus a1bn minus 1 plus a2bn minus 2 up until an minus 1 b1 an b0 x to the power of n plus the rest. Okay? This is called the Cauchy multiplication of two series. Okay? What does this mean? It means that if we have a power series, okay, and we know its interval of convergence, instead of this variable x, we can plug continuous functions. And as long as the values of that continuous function remains inside the interval of convergence of the series, that new one is also working and is something meaningful. Let's see some examples. How can you represent this as a power series? How did you represent it? 1 divided by 1 minus x. This is an extremely important example. You need to know it by heart. It was x to the power of n from 0 to infinity, which is 1 plus x to the power of 2, x to the power of 3. For which values of x? This is important. Not only you need to know what it is represented, but you need to also know for which values of x it is a valid representation. For absolute value of x, less than 1. Okay? Now, is minus x, f of x equal to minus x, a continuous function or not? Minus x is a continuous function, right? As long as the values of minus x is inside the interval of convergence of this power series, which will be which interval? Here, instead of x, I need to write minus x. And which interval this is going to be? This is going to be, again, the same interval. Okay? Again, for these values, when value of x is between minus 1 and 1, what can I do? Instead of this x, I can replace it with minus x, like what we have here. So this will turn into 1 plus x. And what will be my series here? Instead of x, you write minus x. It's going to be minus x to the power of n, right? Which we can represent it as minus 1 to the power of n, x to the power of n. Okay? Which will be what? Instead of x2 plus minus x, this is going to be 1 minus x plus x to the power of 2 minus x to the power of 3 plus x to the power of 4 and the rest. And this is valid for which value of x's? For values of x's which are between. Okay. Again, look at this. This is again a power series, right? A power series, and we know that its result is going to be this. If here, instead of x, I plug x to the power of 2, what will happen? Is x to the power of 2 a continuous function or not? Let me clean here. Is x to the power of 2 a continuous function? F of x equal to x to the power of 2? Yes, it is a continuous function. So I can plug it here instead of x. And it is going to be valid for which values of x? Here. In this one, instead of x, I'm just going to plug x to the power of 2. Which means that for the values of x's such that x to the power of 2's absolute value is less than 1, I can plug here instead of x, x to the power of 2. And this is equivalent to what? This is absolute value of x to the power of 2. You can take square roots, and this is going to turn into absolute value of x less than 1. Which means that again, on the same interval, from minus 1 to 1, if we plug instead of x and x to the power of 2, we will have 1 plus x to the power of 2, which is going to be what? Equal to, instead of x, just write x2. And what will this be? X to the power of 2n. It's going to be x to the power of 2. Which we can represent it as what? 1 minus x to the power of 2 plus x to the power of 4 minus x to the power of 6 plus x to the power of 8, etc. Okay? These three series are going to be super important for us. Especially this one, which we are deriving all of these things. Here, by the way, instead of x, we can also plug directly minus x to the power of 2. And again, the same interval, you will see that, okay, this is going to be equal. Is this something familiar to you or not? Why we are doing this minus x and x to the power of 2 to come derive this one? Does it look like the derivative of something? Your irregulars. Okay. This is actually derivative of arctangent. Okay. Derivative of arctangent of x is 1 divided by 1 plus x squared. Okay. You will see. We will talk about taking derivatives and integrals of power series. Okay, and this kind of functions. Then here we will use that. So please remember what is happening with this one. Okay. By the way, we have always worked with the power series, right? Now we are showing them compactly as a function. Or we are saying that this function is represented as a power series which looks like this in this interval, right? For this function, we call it the generating function of this power series. This is the generating function of this power series. This function is the generating function of this power series. Okay? Good? Now, an important question that we ask ourselves is this. Which kind of functions are there that we can represent them as power series? Because, you know, power series are very nice objects to have. When you're looking at them, as you have seen, we were trying to some kind of make approximations of our functions, right? With 1 plus x plus x2. What is happening here? Around some point, I'm actually encoding some information about the function. Look at it as some kind of layers of information locally around something. If you go and look at the very basic layer, for this function, for instance, at the point 0, what is this number? It is the value of this function, right? What about the next one? If we take these two, not only we are seeing the value of function, but we are some kind of having one level of more zoomed out, and we are seeing how linearly this function is represented. So which means that around the point 0, if you zoom inside and you try to see how this function is looking like, it is linearly looking like 1 plus x. If you want to understand how quadratically this function behaves around point 0, if you zoom in, you will see that it is behaving like this function. Okay? If you want to see more and more geometric structures, okay, you need to just look at more and more terms of power series. That is why power series representations are very important for us. But question is this: can we represent all of the functions as power series? And if we want to do this kind of representation, around which points we can do this? For instance, this 1 divided by 1 minus x is represented as a power series around the point where 0. What about other points? Can we also represent this function as a power series around some other point? This is a really, hard of a problem, but a problem that we need to be very careful about it. It is an important problem. We need to understand what is happening here. Okay? This question actually brings us to the problem of analytic functions. What is an analytic function? Let me just write the definition then. We call a function f from u to c. Okay? This can either be a complex valued function on some domain on the complex plane, or you can select this as, some real valued function from some interval to the set of real values, okay? It's called analytic on A in U if it can be represented, or let me just write this, if there exists r greater than 0 such that for x's with or with z's whatsoever, it doesn't matter, x minus a less than r, we have f of x equal to n from 0 to the infinity of c n x minus a to the power of n. Is analytic n if for all a in U. There are two concepts here. First of all, a function is called analytic at one point if around that point, you can find an interval or a disk such that you can represent this function as a power series over there. A function is called analytic on a set if for all points of that set you can find different values of r, okay, such that around each one of those points there is this disk or there is this interval such that on that interval or on that disk this function is being represented as a power series.